All right. So this is all kind of a undergraduate review and me standing on my soapbox about labeling your strain. But now we're going to set out to derive three-dimensional strain measures. Okay? And we'll also see that the strain measures that we derive will be, sort of graduate school versions of the strain measures you have previously looked at. And I'll show you, we won't get to it today, I don't think, but I'll show you that the sort of undergraduate strain measure that you looked at before, its real name is the infinitesimal strain. It only, it doesn't work, and we'll see why it doesn't work, or it has issues for large deformations. So in the infinitesimal or undergraduate strain is only really applicable for small deformations. And when I say deformations and not strain, I'm not saying small strain, I'm saying small deformations, because deformation would include motion. And so what we'll see in the next class is that if you only have a tiny bit of strain, but then you have a rotation, for example, then that will really throw off your infinitesimal strain measure. So the strain measures that we're about to derive are, the fully nonlinear, most rigorous definitions of strain. And often what we call this is the finite deformation strain measures. Okay, so finite deformation or large deformation strain measures. Finite is like as opposed to infinitesimal. Right? Okay, so let's talk about coordinate frames for a second. Or I shouldn't say that. I don't like to say that. I'm going to say configurations. I'm going to say configurations. So we're going to start with the body. Continuum mechanics, you always draw potatoes. How many potatoes did you draw in your class? A lot of potatoes, huh? Yes, yeah, always draw potatoes. The potato just represents an arbitrary thing, right? It could be this microphone, it could be the table, it could be a car, right? Just a thing. And we often draw it kind of like that. It looks like a weird looking potato. So before, again, and with the caveat of what I said earlier about, often we call the reference configuration the undeformed configuration, but we know that, it's really undeformed is relative because in the Earth, everything is deformed, right? It's just kind of like the reference configuration is probably the more accurate term. It's like where we're going to start from, okay? Yeah, this microphone used to be an ingot of steel. We're not starting there, right? We're starting, the microphone looks like the microphone. Right? So we're going to call this the reference configuration. Again, also you'll see this in the literature as the undeformed. And I put it in quotes because of the caveats I just spoke about. And then again, the Lagrangian. So you'll see in literature, in books, all three of those, they mean the same thing, right? Before the deformation that we're interested in starts, okay? And so then we're going to deform that body into something else. New potato. Same potato, we just deformed it, okay? And then here we'll call this the current or the deformed or the Eulerian. And of course, Lagrangian comes from Lagrange, and Eulerian comes from Euler. Right? It's named after people. Right? And okay, and so what the goal of kinematics is, right? Ultimately to develop strain measures, is to track line segments, right? Because if I can track a line segment, and what I'm going to do is I'm going to write, in this case, we're interested in like infinitesimal line segments. So if I can track a line segment from the reference configuration and then the same exact line segment in the current configuration, and I'm always going to try to use the symbols, uppercase symbols for things in the reference configuration and lowercase symbols for things in the current configuration. So that's D capital S, and I'll try to, in this case for the S, I put the little ligatures on there, like it's a little bit hard to write to see what a difference in a capital S and a lowercase s. But in that case, I put the little ligatures on the S so that you know, or I don't know what you call those, font, some pieces of the part of the font. And then over here is the little s, D little s, lowercase s. Okay, so again, reference configuration, always capital, uppercase symbols. Current configuration, lowercase symbols. Okay, so that's the same line segment, right? Even though I drew it differently because it deformed, right? So it deformed from the reference to the current configuration. And if we can track line segments, well, we can track areas and volumes, right? Because if I can track one line segment, I can track two. If I track two line segments, I can take I can take and get like a parallel piped area from them, right? Or if I can track three, I can track three orthogonal vectors, and then I can understand volume changes, right? If I know three orthogonal vectors in the reference configuration, and then three orthogonal figures in the current configuration, then basically I can take a scalar triple product of either one of them, and that gives me the volume, right? They're vectors, right? So take a scalar triple product, get a volume, and then I know the volume in the reference and the volume in the current. Right? So if I know how the volumes change, then I can begin to compute things like volumetric strain, right? Just like in one dimension we have a linear strain, change in length over length. We have a volumetric. The notion of a volumetric strain too is like change in volume over initial volume. So that's the goal of what we're doing here, is to track line segments. All right. I'm going to try to do this without redrawing my potatoes. So you heard me kind of misspeak at the beginning, and I said reference frame, current frame, or Eulerian frame. You'll hear this a lot. You'll see it in literature. People talk about the reference frame or the current frame. But there's only one frame, right? There's like one inertial reference frame. And in this class, we're mostly going to deal with just the orthogonal Cartesian reference frame, right? So this is like, what we'll call x1, x2, x3. And I'm going to try to always use, for reasons that'll be clear when we get into additional notation, I'm always going to try to use 1, 2, 3, but you can also think of it, and perhaps sometimes I might say x, y, z, right? So there's just one frame. That's our, fixed inertial reference frame. And so that's why I kind of caught myself and I said, okay, I don't want to call it reference frame. I want to call it the reference configuration, right? So how we orient things in the two configurations, everything is going to be with respect to a single frame, right? This inertial reference frame. So what we're going to do, or we're going to start with, is we're going to basically pick 2 points in my reference frame. I'll call them X. This is, as you'll see, and Q. Again, I'm using capital symbols. In this case, I'm writing a vector over the top of them because they correspond to vectors that originate from the reference frame, or the inertial frame. And so I have a vector X, and I have a vector Q. in the reference frame, and under deformation, right? So we're going to deform our reference configuration into our current or deformed configuration, and we can track that. You know, if we basically track the displacement of each of those points, right? Again, you know, it would be just like if I drew a dot on the side of the car and then I smashed it with a hammer. Like, the dot's still going to be there. It just might be in a little different place. Right? So we're just going to track our dots from the reference configuration to the current configuration. Each of those are going to have displacements associated with them, right? So if Q ends up over here in our current configuration, and I'll use a little q, then the displacement associated with that would be this vector. And we often use the symbol U, or the alphabet letter U. Again, it's a vector. And just to be explicit, I'll write it such that it's a function of Q and T, right? So the displacement is a function of where it was and time, right? Where it started and time. Okay. Same thing with the other one. We'll say that X moves to here. Again, little x vector, and we have a displacement associated with that. U of X and T. So now what I want to do is I want to write, these are just vectors, so I can just do vector math, right? So I want to write the position of X and the position of Q in terms of their original position and their displacement. So I just add vectors, right? So I don't, I may not know what this vector is yet, but I know that vector is X, and then I have U of X and T, so I can write X in terms of big X plus U of X and T. I can likewise write Q in terms of big Q and U of Q and T. And maybe just to add a little clarity, I'm going to write this in X, and I'll write, so that's this, right? And that is that. All right. So remember what I said, that we're interested in tracking line segments? Right? Well, can anybody identify from the labels I've written on these two configurations what a line segment is in the reference configuration? Well, that is one. I mean, that was kind of separate there. But what I'm saying is, like, ignore that for a second, and just like terms of X and Q and U, right? Would you agree that a line segment is Q minus X? Right? This is a vector, like Q minus X. So there's a line segment in the reference configuration that's Q minus X, and then I got a line segment over here that's little q minus little x, right? So let's write down what this line segment little q minus little x is in terms of things in the reference configuration and their displacements. Okay? So I'm going to write down q minus x is equal to u of q, and I'm going to drop the t just for a little conciseness in the notation, but it's actually the other way. Let's see. So we have should we the other way? Yeah, you're right. Yeah, sorry. Okay. So now what I want to do is I'm going to do a Taylor expansion about the point Q equal to X. And to do that, remember these are vectors, right? So there's actually three components to this, right? X1, X2, X3, Q1, Q2, Q3, right? So there's three components to that. And what I'm going to do is I'm going to write basically the Taylor expansion in terms of the ith component, right? So just arbitrary ith component. So I could be 1, 2, or 3. Okay? So I'm going to write in terms of that, and you'll notice then I drop the vector because now I'm just talking about a component. Okay? When I do the Taylor series expansion, Qi minus Xi then I get Qi minus Xi, big Xi, plus partial Ui partial big Xj Qj minus Xj. That's just the first term. Then plus partial squared Ui partial Xj partial Xk times Qj minus Xj times Qk minus Xk. And so here we're starting to use, and in more terms, right? So plus HOT. What does HOTs mean? Higher order terms, right? So we could go, and it's a Taylor expansion, it's infinite, right? So I could go on and write all the terms forever. All right. A couple things here. So we started to write things in terms of components, okay? And so this is where my I's and J's come in, because I, J, and K all just go 1, 2, 3, 1, 2, 3, okay? But there is an implicit, like an implicit summation, and I'm going to write things out. I'll do one example in a second, or maybe next class, where I write all the components out. But whenever you see a repeating, whenever you have a term whenever you're using additional notation like this, which is ubiquitous in continuum mechanics, whenever you have a term, and a term just means like something separated by, product multiplication separated by addition and subtraction. So like this is a term, right? This is a term. Whenever you see a term like this and you see a repeated indice, see how the J's repeat? That's an implied summation. Right? So if you had, like for example, a dot product, right? So if you had two vectors, if you had a vector A, and it has three components, right? So it's like A1, A2, A3. And you had another vector B, it has three components, B1, B2, B3. And you will take the dot product, right? So it's A dot B. That's equal to A1, B1 plus A2, B2 plus A3, B3, right? That's the dot product of two vectors. Or another way to write that would be the sum of AI, BI, where I goes from 1 to 3, right? So what we do, and it was actually Einstein that was kind of the originator of this notation, what we do is whenever you have a repeated indice, so you see how this indice is repeated, the II, that implies the summation. So to make our notation more concise, we just get rid of the sum, and we write this as simply AI, BI. So whenever you see a repeated indice, it implies summation. So I'll write that out. So in indicial notation, repeated indices in terms, remember what I said a term is, imply summation. So, like another rule that's just kind of closely related to this is that you cannot have more than two repeated indices in a term. It wouldn't make sense. So you could not have, like, for example, here. So here you have, up here you have xj and j. So the j is just repeated once, and this is two terms, right? Because you have this multiplied by that, and then this multiplied by that, right? So if you separated that out, that would be a term, and that would be a term, and so you have only one repeated indice, and that's the j. So like if it was uj xj times qj, that doesn't make sense. Right? So you can only have one repeated indice per term, and that's the indice that you sum over, and the other indices that are not repeated are called free indices, and those represent equations, right? So if we wrote down, if we let qi equal to 1, we wrote that down, we basically have a summation over j, and we're gonna do this later. but just so you know now, we'd have a summation over j, but the I would be a free indice, and that would represent an equation, right? So you'd have one equation for I equals 1, and then you have another equation for I equals 2, and another equation equals I over 3. And each of those equations would have a summation over j equals 1, 2, 3 in there, right? So really what this represents, this is a matrix, that's a vector, and this is a matrix vector product. And we'll see that again. I'm going to, at least for one example, I'll write out all the terms. All right? But what I want to do is I want to further simplify. So I kind of took an aside there, but let's go back and look at this equation. And I'm going to write it again down here. I'll write Qi minus Xi, that equals to, now I'm going to do something a little bit different here. I'm going to say delta Ij Qj minus Xj plus partial Ui partial Xj Qj minus Xj plus HOTs. Now, what is this thing? Kronecker delta, right? So it's this special thing that is 1 when I is equal to j and 0 otherwise. So, for example, I could write AI is equal to so I have sum over j, but this thing is 1 only when I equals j, so therefore this equals AI. Right? It kind of works like an identity matrix. That's what it does. Right? And we'll see that again when we write out all the terms. You'll see how it kind of appears as just like ones on the diagonal. Okay. So then, finally, one more time, I'm going to write this down as, because I wanted to write it like this, so that these two terms are common, right? So that I can pull out this thing, right? So I'm going to write Qi minus Xi is equal to the Kronecker delta plus partial Ui partial Xj times Q times Qi minus X. Sorry, Qj minus, keep hitting the erase button. Qj minus Xj plus higher order terms, or another way you might write it is terms that are on the order of Q minus X, where this is like an L2 norm of those two vectors. It's like a measure of the distance between those two vectors. Difference between those two vectors. Okay. So, all of that was written in terms of my arbitrary points Q and X in the reference configuration, and Q and X, little q and little x in the current configuration. And I didn't say how far Q and X were apart from each other, right? I just drew two dots, okay? But now what we'll do is we're going to go back and we're going to say that these 2 points are infinitesimally close to each other, right? And that vector, Q minus X, we're going to call dx, d big X, right? And then over here, this vector, little q minus little x, we'll call d little x. Okay? So all we did, when we initially wrote those down, we just Q and X are just 2 points. Now we're going to say those 2 points are infinitesimally small, right? Infinitesimally close to one another, right? So turning over here, remember I said little q minus little x is dx, and big Q I'll be done in 1 second. Just bear with me. Is big dx, right? And because they're infinitesimally small, this thing doesn't matter, right? The distance between two infinitesimal, if this is infinitesimally small, right, then higher order terms on the order of this, we're going to assume are 0. And so now, finally, in component form, we have dxi okay, or in vector form, we'll write d little x is equal to the identity matrix plus, let's do it this way, plus grad u, grad with respect to big X, grad u transpose. We'll see why it's transposed next time, dx, right? So remember what I said, our goal in kinematics is to track line segments from the current configuration to the from the reference configuration to the current configuration, right? This is an infinitesimally small vector in the reference configuration. This is an infinitesimally small vector in the current configuration. This is the thing that takes a vector, it's a map, right? So it takes a vector in the reference configuration into a vector in the current configuration. This thing is called the deformation gradient. We often use the sign F for that, F. And so again, this will be the last thing I write. dx is equal to F d big X. This is the deformation gradient. In continuum mechanics, it is the most fundamental quantity, and it's fully nonlinear, right? It does imply that the vectors are small, and so it implies like only within a small neighborhood of the reference configuration, right? But within that, it's a fully nonlinear mapping that takes a vector in the reference configuration into a vector in the current configuration, right? It's the most fundamental quantity of deformation.